Welcome back, everyone. This is Professor Herring. In this video, we're going to learn about organic chemistry. While this introduction is going to be somewhat brief, it's going to provide you with an important overview of the different classes of hydrocarbons, understanding geometric and constitutional isomers, and then we'll eventually look at functional groups as well. Let's begin. First thing I want to point out is that organic chemistry is such an important subfield within chemistry. There are nearly 10 million organic compounds, and these compounds have so many different uses, and there's so much organic chemistry around us in the world that our societies would not be the same without it. And just to give you a very, very brief overview of what we mean by organic chemistry, we're talking about carbon-based chemistry. And generally speaking, we're not talking about metals involved. However, some metals do interact with organic-based compounds. We're generally talking about things that involve the elements carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. We'll sometimes hear that referred to as CHNOPs. So let's just take a look at some really cool organic structures. The largest protein is one that's called titin. And I'm not going to read off to you the molecular formula, but you can see that it literally has hundreds of thousands of atoms within a single protein. And it has a molar mass of 3.8 times 10 to the 6 grams per mole. And while this is massive, there are in fact molecules that are even larger than that. The largest human-made molecule is called PG5. This was synthesized in 2011, and it has over 15 million carbon atoms and 40 million hydrogen atoms. And while it doesn't look very big in this structure, that's because if you notice down here, what it's showing is this symbol, and it has the structure, and then it continues on. And it turns out that there's 170,000 of these molecules bound together to form PG5. And it has a molar mass of almost 100 times more than the largest protein, titin. And if you think that's impressive, our body is made up of DNA, right? Well, if you take a look at the X and the Y chromosome within humans, those are 100 times more massive than PG5. And so the organic world is complex, it's varied, and it's super important to our daily lives. So we're going to begin by looking at classes of hydrocarbons. And hydrocarbons are molecules that only have carbon and hydrogen in them, hence the term hydro and carbon. And there's four main types. We have alkanes, alkenes, alkynes, and aromatic compounds. And you'll notice that for the first three that there's a very subtle difference. There's just A, E, or Y. And those three indicate essentially the level of what we call saturation. Alkanes are fully saturated. They have all single bonds. And what it means to be saturated is that there's the maximum number of hydrogen atoms attached to the carbon backbone or skeleton. There's no rings, there's no double bonds. Whereas in alkenes, we have one or more double bonds, as indicated here, and alkynes have one or more triple bonds. Aromatic compounds have an alternating double single bond structure in a ring. And we talked about before how this means that they exhibit resonance. Now, something to note is that you can have multiple classes of hydrocarbon within a given structure. So let's say that we had this structure. Oops, let's draw that again. So this molecule has regions that are alkanes, alkenes, it has an alkyne in it, and it has an aromatic structure. So they're not mutually exclusive, and we mostly just want you to understand the terminology and know how to recognize them. Alkanes, in fact, any hydrocarbons can be straight chained or branched. So this is the same molecular formula, but you can notice that we have a different arrangement. We call these constitutional isomers. They're also sometimes called structural isomers. And that's where they have different, same molecular formula, but the atoms are bonded differently to each other. And within constitutional isomers, what we can see is that the larger the molecule, the more complicated it is, the more numbers of constitutional isomers we can get. And so you'll get some practice on the homework drawing different constitutional isomers. My recommendation is to count up the longest chain branch and then essentially remove one of the portions and attach it to a different location. And by doing that in a kind of a systematic way, you'll be able to draw the various isomers. Alkanes are also free to rotate around. So these are just different ways of representing the same structure. So even though these look potentially different from each other, these are actually the same molecule. These have 1, 2, 3, 4, 5, 6. So this is a C6, H14. This is hexane. And this is essentially just hexane rotated in different ways. Think of it like you standing up tall, you slouching over, you laying down, you curling up into a ball. It's all you, but there's just different ways of representing that, different ways of arranging that. And so those have different conformations. Another thing to point out is that we use these dashes and wedges to indicate directionality of bonds. So in other words, these molecules are not just flat. We know that this carbon really has 2 hydrogens bound to it in addition to the other 2 carbons. And therefore, since it has 4 electron domains, we know that it's tetrahedral. Well, if it's tetrahedral, it must have a 3-dimensional structure. And that's what the dashes and the wedges are used to indicate. The wedges indicate that it's coming out of the screen. Or paper. And the dash indicates that it's going into the screen or the paper. And you don't need to worry so much about you being able to represent it in 3 dimensions. However, if you can, then that's going to help when it comes to trying to determine molecular polarity. It makes it easier to visualize it. Let's move on to alkenes now. So one of the simple alkenes is called butene. Butene, as the ene indicates, is an alkene, which means that has a double bond. And so butene has 4 carbons and and 1 double bond, but we can represent the same molecular formula in 4 different ways. And we talked earlier about constitutional isomers as being molecules with the same molecular formula, but different bonding patterns. However, when you take a look at these two, and if we were to label these as carbon 1, 2, 3, and 4, 1, 2, 3, 4, we see 1, 2, 3, 4, 1, 2, 3, 4. We see that in the first 2 cases that we have different bonding patterns. carbon 2 is now bound to carbon 4. And the double bond was between 1 and 2 and is now between 2 and 4. But in this case, carbon 1 is bound to 2, which is bound to 3 and bound to 4, which is the same here. Carbon 1 is bound to carbon 2, bound to carbon 3, bound to carbon 4, and the double bond is still in between the same two carbons. However, there is a different arrangement here, a different geometry, if you will, and that comes because we talked about how double bonds don't freely rotate. We talked about how that's because in order to form a double bond, you need a pi system, and they overlap above and below, and so if you rotate, then you break the bond. So this gives rise to what we call geometric isomers. And geometric isomers are pairs of molecules that only differ in the geometric arrangement of the groups around the double bond. In other words, it's what we saw just here. It's the same bonding pattern. 1 is bound to 2, bound to 3, bound to 4. The double bond is in the same location. But the relative orientation of 1 to 4 is different. And so it turns out that these geometric isomers are chemically different molecules. They have their own unique properties. They're different from each other in the same way, in a similar way, that 1-butene is different from 2-methylpropene. So let's explore this idea of geometric isomers a little bit farther. So we use the terms cis and trans. Trans you can think of as meaning across, and cis meaning same. As in, the Transcontinental Railroad crosses the continent, or a transatlantic ocean liner is going across the Atlantic Ocean. And cis, the way that I remember cis, is the sound. So it makes this sound, as does the word same. So cis is on the same side. And so when we look at these cis versus trans configurations, you have to cross the double bond for these groups to get from one group to the next. Whereas in the cis configuration, they're on the same side of the double bond. You don't have to go across the double bond, but it's in fact on the same side. And so what this looks like in 3 dimensions is if we were to look down at the double bonds, these other groups, it's where they are in relation to each other with respect to the double bond that tells us whether or not we have a trans formation or configuration or a cis configuration. So let me give you an example here. If we want to determine whether a molecule has a geometric isomer, what we're going to do is find the 2 carbons that are within the double bond. Let's call those carbon A and carbon B. And in order to have a geometric isomer, you need to have the groups attached to carbon A. So the groups must be different. The groups on carbon A must be different from each other. In other words, in this example, 1 must be different from 2. You also have to have groups on carbon B must be different from each other. So 3 has to be different from 4. Now, it turns out that 1 can equal 3, and that's okay, or 2 can equal 3, and that's okay, or 1 can equal 4, etc. But the groups on the same that are attached to the same carbon must be different. And in both cases, if 1 is different from 2 and 3 is different from 4, then that molecule can have a geometric isomer. So to make that geometric isomer, what you'll do is the following. you keep one of the two sets the same and rotate or swap the other two to make it as if we swap the location of 3 and 4. These two molecules then these are geometric isomers. So let's practice this on actual molecules. Which of the following have geometric isomers? Well, the first thing you want to do is find the location of the double bond, right? We can label these as carbon A and carbon B, and then we want to evaluate, are the groups on A the same or different? Are the groups on B the same or different? Both sets must be different. To have a geometric isomer. So let's evaluate. On A, you have a large carbon chain and a hydrogen. So those are different. On B, you have the same group. They're the same, and therefore this molecule cannot have a geometric isomer. And the reason why, or rather, I guess you could test it out. You could try and rotate the groups on either side, swap places, and you'll end up with the same molecule. So if we swap the groups, we get the same molecule. In other words, it's identical. Let's try the next one. So if we look at the two groups on this carbon, we see that they are indeed different. There's one carbon on one case and the two carbons with its hydrogens on the other case. The other one is, in fact, the same. So in other words, this is the groups on carbon A are equal to groups on carbon B, but that's okay so long as within those groups they are different. And so the geometric isomer of this would be taking and rotating. We'll just label this C and D. Now we have D up here and C down below. And we can see then that there's a different relationship between these different groups than there used to be. Looking at this, along this double bond, those two groups are different. We have a hydrogen and then this large aromatic ring. Looking on this one, it's maybe a little bit more difficult, but because you can see it's in a ring, this is the same as this, this is the same as this, and then there's only one group there. So the two groups on either side of that carbon are the same, therefore it cannot have a geometric isomer. In this one, we see that, similar to the one on the left, those two groups are different from each other. And now we've added this chlorine group on. So while this group is the same as that one, this group is not the same as that one, and therefore it meets the criteria. It's different. And this can have a geometric isomer, which would look like the following. Again, this all arises from the fact that the double bonds do not easily rotate, and therefore we can create different molecules that have different chemical properties. Let's talk now about saturation versus unsaturation. If it's an alkene, an alkyne, or a cycloalkane, then that produces what we call unsaturation. You'll sometimes hear referred to as degrees of unsaturation. And so if you've ever heard of saturated versus unsaturated fats, all that's different between them, if they have the same number of carbons in them, is whether or not there's a double bond or a single bond. And this has important effects on the structure and the function of those molecules. So stearic acid is straight chained, whereas oleic acid has that kink in the chain due to the double bond. And what that does is it changes their properties, such as the melting points. So stearic acid, because it's able to form the straight chain, it's going to have a higher melting point. It's going to have more interactions than with the not straight chained oleic acid. Those aren't going to interact as well. And maybe some of you, as you're looking at this, if you're Pokemon fans, you maybe see that Caterpie in there. But the point here is that the structure affects the properties. And we're going to get more into depth into those forces in Chapter 11. Structure also is going to determine its reactivity. We saw already that aromatic compounds, because of the resonance, are more stable than compounds that are not aromatic. But we see that the presence of the double bond is going to affect the reactivity of hydrocarbons. And so if you take a regular straight chain alkane and react it with bromine, nothing's going to happen. But you can get a chemical reaction when you react it with an alkene or an alkyne. And so if we take, say, a compound that involves, or a fatty acid that's unsaturated, we're going to get a chemical reaction. So all of this is to demonstrate that the structure matters, that whether it's an alkane, an alkene, or an alkyne affects the chemical properties of the molecule. And hopefully you saw as we went along that because of the different nature of the double bonds, whether there were double bonds or triple bonds in the molecule, that's going to affect its hybridization. And so this kind of summarizes here for us the hybridization that we can see within the different classes of hydrocarbons. For alkanes, because there's 4 electron domains, they're all sp3 hybridized. Whereas alkenes are going to have sp2 hybridization at the double bond and sp3 hybridization in other locations where there's not double bonds. Because there's 2 electron domains within the alkyne, it's going to be sp hybridized. And aromatic, because it has 3 electron domains, that's going to be sp2 hybridized. So that's it for this video looking at classes of hydrocarbons. If you have questions, you can ask on Piazza, in office hours, or in recitation. Thanks for watching and have a great day.